If anybody has one particular question about the inverse function theorem exercise, I can do that. Yeah.
I don't understand two parts 2 and 3.
Okay.
Oh wait, no, I understood.
Basically, question 2.
Yeah.
Basically, question okay. So in question number 2, we had f of x, and we were supposed to find f inverse and we find the derivative. The intent of this question is that if you find the derivative by solving for f inverse and then taking the derivative of that, you should get the same answer as if you do it with inverse function.
Okay.
That's the intent. So to find f inverse, we're talking about solving. If I begin with y equals f of x, and I solve for x, and then swap x and y, then I'll have my inverse function. You can reverse the order of these. You can swap x and y first, and then you will have an implicit function that is your inverse. So if I swap x and y first, now I've got my inverse, but it's implicitly defined. So if I want it to be explicitly defined, I'm going to need to solve by subtracting 6 from both sides and dividing both sides by 3, and there is my f inverse of x. I need to jump up and down and fuss a lot to emphasize that this is not a reciprocal. So if you told me that the inverse was 1 over 3x plus 6, you missed the whole point.
Right.
Right.
Right, yeah.
Okay,
yeah.
good. Now, what is f inverse prime? Since I have f inverse, I'm just taking the derivative of this guy.
Part 2, technically.
Yep. And I think the easiest way to do this is to recognize I have a constant of 1/3. Out it comes with the constant multiple rule. And the derivative of x minus 6 is easy. So that the derivative of my inverse is equal to 1/3. And we're done. So that takes us up through part 2. Okay? Now, part 3 asks you to come back and compute the same thing, f inverse prime, but using the inverse function theorem. So, we could have gotten f inverse prime by rewriting it as 1 over f prime of f inverse of x. So that takes me back to the question, what is f prime? And f was 3x plus 6. So f prime is equal to the derivative of that, which is simply 3.
Wait, how?
Because f of x was 3x plus 6. So you got to keep your eye on the ball. We've got two different functions going here. We've got f, and we have its inverse. And this is f, and that's its inverse.
So the inverse is, so it's 1 over 1/3, basically. And now?
No. Don't make it too hard. This is f. What's f prime?
3 plus 6.
So what's f prime? Yeah, you're trying to bring in extra stuff here. Just focus on the really narrow question. I give you f of x equals 3x plus 6. What is f prime?
3.
Yeah, that's it.
How did you get that? Oh, but are you not using the equation?
No, I'm preparing to
you were
use the
putting it in the
equation.
equation for some reason. Oh,
I'm going to be putting it in just a minute. Yeah, that's right.
Okay.
So to get our f prime, I don't use the equation here. I use what f is, and I take its derivative.
Okay.
And that's simple enough. Yeah. Now that I've got f prime, here's the tricky part about this whole question. For what values of x does f prime equal 3?
All of them.
All of them. That's right. Including when x is f inverse or whatever. Doesn't matter. So that I immediately plug in 3 for f prime. What is f prime? I need
But
3.
but why would is f prime of f inverse?
Doesn't matter.
Oh, it's just
What's f prime of anything?
Oh.
3.
Okay.
Yes, f prime is a constant number.
Okay.
Because my function was a constant, was a slope of the constant.
Oh, because of the
A
wind.
logarithmic constant slope. Because of the
Okay.
linear. That's right. If my function had been something more complicated, then I would have had to actually put in f inverse into my formula here. But when I put in f inverse right here, I still get 3. So there it is. I think you had a double reciprocal going on.
I need to know where the f prime is constant.
Yes. I don't have a lot of time to do that. Oh, sorry. Actually, we're going to be doing the 3 as part of today's lesson, so that'll work. All right? On we go. Here's our goal for today and tomorrow. Our goal for today and tomorrow is to become good with inverse trig functions. And today, I want to focus mainly on the algebra and a little bit on the calculus. Tomorrow, we're going to do a lot of calculus. So that by the end of today, hopefully we can use them to solve. Hopefully we can draw their graphs. And maybe we can get their derivatives. All right? That's our goals. And let's see if we can make all of that happen. What I would like to do is to have an inverse for this function. But immediately, I have a problem. What does the graph of y equals sine x look like? Right. Does this thing pass the horizontal line test? No. Does it have an inverse? No, it does not. So in order for me to get a function that actually has an inverse, what I'm going to have to do is to restrict the domain. And I'm going to restrict the domain to a portion of the graph for which sine of x is always increasing. And that is going to be from the bottom to the top. What is the angle right here at the bottom? Where is that point on the graph? Everybody mark the coordinates of this point on the graph. And when you're done, mark the coordinates of that point also. Hint, what's the y value at the bottom? -1. So what angle reduces -1 in sine? Should be -π/2, that's right. So this is going to be from x equals -π/2, π/2. And we are going to extract out of sine x just that little portion of the graph. And that's going to give us a new function, which we sometimes call capital sine of x, which is sine x on the restricted domain -π/2, π/2. And we're talking here about quadrants 1 and 4, π/2, -π/2, quadrants 1 and 4 on the unit circle. These are going to be the only quadrants we consider because that is the largest domain that I can find for which sine x is 1 to 1. Everybody with me on the concept? And so now I can define an inverse. If this is f of x equals sine x, then f inverse of x, which is inverse sine of x, is now going to be a function that takes values from -1 to 1 and gives back the angles that they came from. That's the purpose of inverse trig functions. It takes trig ratios and gives you the angle that they came from, but only an angle in the first or fourth quadrants. takes a ratio in the domain negative 1 to 1 and gives an angle from negative pi over 2 to pi over 2. How do I actually compute the inverse trig functions? Well, I actually can't compute them for very many of them. For most of them, I just have to leave them like they are. In the same way that we don't actually compute very many square roots. If I solve an equation and I get x equals square root of 65, you probably don't turn that into any sort of decimal equivalent, right? You probably leave that as the square root of 65. In the same way, if I have an equation, sine of x equals 0.2, I can take the inverse sine of both sides, and on the left-hand side, boom, inverses cancel, because that's what inverses do. And on the right-hand side, I get this value, inverse sine of 0.2, and that's a number, but I'm not going to be particularly interested in finding out its decimal approximation unless I really need to. The calculator can give you decimal approximations. If you don't have a calculator, get that out and find the inverse sine of 0.2. Make sure you're in radian mode or you'll get the wrong answer. Takes a ratio. All of your sines are ratios of opposite over hypotenuse, right? So sine of x takes an angle and gives you the corresponding ratio. The inverse sine flips that around. It takes the ratio and gives you the angle that corresponds. So what value do you get for inverse sine? Either one of these would be perfectly acceptable as an answer to the problem. But it's only valid for the first and the fourth quadrants. Notice that the inverse sine of a positive number is going to give me a first quadrant angle. If I take the inverse sine of a negative value, go ahead and do that, and you should get an angle in the fourth quadrant. What did you get? Is that an angle in the fourth quadrant? Yes, it is. Negative angle would send you below 0. So this gives us an angle in the fourth quadrant from negative pi over 2 to 0. Okay. Now, we can do the exact same thing for all of our 6 trig functions, and we will. But we're going to have to be tricky about the domains that we use for them. So let's consider domain and range for each of our 6 trig and inverse trig functions. We've already done sine of x, so its domain that we're going to restrict to is negative pi over 2 to pi over 2, because we're trying to limit ourselves to a domain for which sine is strictly increasing, so that it will be 1 to 1, and its range is negative 1 to 1. When I invert that function, inverse sine, then I'm going to swap domain and range, because all of the y values for sine now become x values for inverse sine, and all of the x values for sine now become y values for inverse sine. So inverse sine is going to take a number between negative 1 and 1, and it's going to spit back an angle between negative pi over 2 and pi over 2. Does this make sense to everybody? We can do the same thing for cosine. But my domain has got to be a little bit different because the graph of cosine is different. Think about the graph of cosine. if I want to invert cosine x, then I'm going to have to choose a domain for which it is strictly increasing or decreasing. And the usual choice is to choose this portion of the domain where cosine x is strictly decreasing, and therefore it is 1 to 1. And so the domain of choice then is going to be 0 to pi. It's going to get the angles in quadrants 1 and 2 right here. And when you take the cosine of those angles, then you get a range that's from -1 to 1. Bless you. So that when I invert, then I'm going to swap domain and range once again. Okay. Here's what I'd like for all of you to do. I'd like for all of you now to sketch a graph of tangent of x. And based on that graph, I'd like for you to decide on a restricted domain that we could use to invert tangent. Go. So it seems that a good restricted domain for tangent would be one that gets exactly one branch of this whole thing. Notice that I am using open parentheses here. How come I don't include -pi/2 and pi/2? Because we have vertical axioms. That's right. And my range, whoop, I did this kind of wrong. Let me do it in the right colors. So my domain is -pi/2 to pi/2. And my range is going to be all the way from -infinity to positive infinity. So that when I invert to get the inverse tangent, then I'm going to get a domain from -infinity to infinity and a range from -pi/2 to positive pi/2. These three are the most important three, and if you understand this concept, then we'll be able to figure out the rest. What I'd like to do at this point, rather than go through all the other three, is to talk about the graphs now of each of our inverse trig functions and see how we can come up with the graphs. May I go on? You good? Okay. The graphs of our inverse trig functions. Technically, I could do this by flipping about the line y equals x, but that's hard for a lot of people to visualize. So if I consider the graph of y equals sine x, capital sine x here in black, on our restricted domain from -pi/2 to pi/2, then my graph would look like this. And students who are really good at picturing this kind of stuff can probably take and sort of imagine flipping about the line y equals x like this. So my graph is even bad. I need to make it go below. There, it's more like that. So they can probably picture flipping about the line y equals x and getting some kind of graph that looks like, see, I'm bad at it too. It's going to look like this, like that. But see, I'm not very good at that. And so what I need to do is I need to have some reference points for myself. And so when I do the graphs of the inverse trig functions, I always choose what I call a 3-point solution. I'm going to pick 3 points that I know really well on the graph of sine. And I'm going to swap x's and y's to get points on the graph of inverse sine. And then I can connect those with a smooth curve. So let's choose those 3 points. And if I go to the graph of y equals sine x, then the 3 points that I know are that, first of all, it goes through the origin, obviously, because the sine of 0 is 0. And then it also goes through the point pi over 2 comma 1. And then it's going to go through the point negative pi over 2 comma negative 1. And those 3 points are easy for anybody to figure out, right? Now if I want my inverse is going to have matching points found by swapping x and y. My inverse is going to exist at the point negative 1, negative pi over 2, and at the point 0, comma 0, and at the point 1, comma pi over 2. And if I plot those points, 0, 0, let's see, pi over 2 is about what number? Give me a quick decimal approximation. 1.6, 1.7. It's going to be a little larger than 1. It's going to be right here. And negative 1, negative pi over 2 is going to be down here. And now I can draw my graph just by connecting with a smooth curve. And I've got it. Ta-da! So we get 3 points, connect with the smooth curve, and we're good to go. We can do the same thing for inverse cosine. Let's choose our 3 points that we know on the cosine graph.
We know 0, 1.
We have 0, comma 1. Good. Cosine of 0 is 1. What else? What are the cosine values you know? Pi is negative 1. Good.
Pi over 2 is 0.
And pi over 2 is 0. So that gives us 1, 2, 3 points. We can now invert those points by swapping x's and y's. And that gives us 3 points on our graph of inverse cosine. And I can now plot those, 1, comma 0. So I go out to 1, and there's 1, comma 0. I go to negative 1, comma pi. So here's negative 1. I go all the way up to pi. And 0 pi over 2 is going to put me right here. Now I've got 3 points, and I can connect them with a smooth curve. And I've got my graph of inverse cosine. That's a strange looking graph, isn't it? Does this make sense to everybody, how we're coming up with these? How about the graph of inverse tangent? Well, I'm going to use the same idea, the 3-point solution, but 2 of my points, instead of being points, I'm going to use the vertical asymptotes. Because tangent, I know, already has vertical asymptotes. Has vertical asymptotes at x equals pi over 2 and at x equals negative pi over 2. And I also know that the graph of tangent goes through the origin 0, comma 0. When I go to invert this, I am swapping x's and y's so that my vertical asymptote x equals 2 now becomes a horizontal asymptote y equals pi over 2. And a horizontal asymptote down here of y equals negative pi over 2. And of course my point 0, 0 is swapped and remains 0, 0. So that the graph of inverse tangent is going to have a horizontal asymptote y equals pi over 2 and a horizontal asymptote y equals negative pi over 2. And it's going to go through the origin. And now I can do a smooth curve that takes me through. Ta-da! Interesting graph. By the way, a fun fact about inverse tangent is that because it has this horizontal asymptote, it actually has a limit at infinity. So the limit as x goes to infinity of inverse tangent of x is simply equal to pi over 2. and I don't compute that limit with any algebraic anything. I simply read it straight off the horizontal axis. How are we doing so far? Okay. I want to show you kind of a cool thing. This is going to be half geometry, half algebra. That was spelled wrong. This is what I call right triangle analysis. And right triangle analysis is going to be used to simplify expressions such as sine of the inverse cosine of 0.5. Something like that. I want you to notice that this is a really weird looking expression. And so we wonder how is this going to happen.
When do you need to know this? When do people use this in real life?
That's a great question. It turns out you don't know yet, but it happens all the time.
Like what profession would, like not just a math profession, but like
Tell me
what
the
profession
inverse
would
of
you
sine
go
of
into?
Yeah.
cosine.
Primarily engineering professions. Other than that, primarily engineering professions is where this is going to show up.
Like in real life.
In real life.
Everything is
In real life engineering. Depending upon the type of engineering. If you're doing software engineering, maybe not. If you're doing anything with mechanical, electrical, you're going to see. Okay. So, the way that we're going to do this, rather than try to do some fancy algebra with it or memorize a formula, is we're going to think of it in terms of a right triangle. We're going to draw ourselves a right triangle that represents the inverse cosine, represents, there we go, the inverse cosine of 0.5, and once we have drawn that right triangle, we're going to find the sine of the angle that goes there. Now, how do I draw this triangle so it represents the inverse cosine of 0.5? The inverse cosine of 0.5 is going to be an angle, because that's what inverse trig functions do. They give you angles. And the angle that we're talking about is the angle in a right triangle so that the cosine of that angle is exactly equal to 0.5. How do I know that? Because if I set theta equals inverse cosine of 0.5, and I take the cosine of both sides, then I get cosine theta is equal to 0.5. Well, how can I arrange the sides in my triangle so that the cosine of theta is equal to 0.5 or 1/2? And the answer is that I can make my right triangle have the adjacent over hypotenuse proportion be 1/2. Why adjacent over hypotenuse? Because that's what cosine is. It's adjacent over hypotenuse. So if I draw my triangle as, for example, 1/2 like this, then the cosine of that angle now equals 1/2. Are those the only choices I could have made? No. I could have made this 0.5 and that one 1. Or I could have made this one 2 and that one 4. Or I could have made any proportional triangle like that so that adjacent over hypotenuse is 1/2. Does everybody see that this triangle right here represents the inverse cosine of 0.5 because the cosine of this angle is 1/2 or 0.5? Am I making sense?
Yes.
Okay. Now what I want is the sine of that angle. And the sine of that angle is opposite over hypotenuse. Well, I don't know the value of the opposite side, but I sure could figure it out, couldn't I?
Pythagorean theorem.
Bingo. Everybody figure it out. That is a 1.
It's a 1. Square root 3.
Okay, and you should have figured out that this side is root 3, am I right?
Yeah.
If you got root 5, you weren't being careful. And so now the sine of this angle is opposite over hypotenuse, which is equal to root 3 over 2. And we're done. So a geometric analysis, not an algebraic analysis, is able to carry this home and find these kinds of expressions. Now, here's one of the interesting outcomes of this right triangle analysis here. Let's take a look at the right triangle. And I'm going to take this angle theta right here, and I'm going to label this side x. Maybe I should call it y. And I'll call the hypotenuse 1. What does this triangle represent? Well, this triangle clearly represents that sine theta is equal to x over 1, right? And therefore, the inverse sine of x is equal to my angle theta. So this triangle would represent the inverse sine of x. Everybody with me? What is the measure of this angle right here? If I'm doing it in radians, these two angles are complementary. They have to add up to 90 degrees, which is how many radians? Pi over 2. So in radians, complementary angles add up to pi over 2. So this angle right here has to be pi over 2 minus x. Just like, minus theta, excuse me. That was 4. Let's try that again. Beep, beep, beep. Shoot. So this angle right here is pi over 2 minus theta. It is the complementary angle. Now, if you take a look at pi over 2 minus theta, you notice that it's adjacent to x, right? So that I could say that pi over 2 minus theta is the inverse cosine of x. Because the cosine of pi over 2 minus theta is equal to x. Does everybody see that? So I have something really interesting. I have an expression for the inverse sine of x, which is theta. And I have an expression for the inverse cosine of x, which is pi over 2 minus theta. Watch what happens when I add them. When I add them on this side, I get inverse sine plus inverse cosine. On this side, look at that. Theta and minus theta cancel. And I get exactly pi over 2. We call this the cofunction relation. It's or cofunction identity for the inverse trig functions. An inverse function plus its inverse cofunction always add up to pi over 2 because they are complementary angles. Inverse sine x and inverse cosine x are two complementary angles that add up to pi over 2. And I could do the same thing, I won't, but I could do the same thing for inverse tangent and inverse cotangent. And I could do the same thing for inverse secant and inverse cosecant. And all three of these together are called the cofunction ID for inverse trig functions. We're going to make use of this fact to cut our workload in two when it comes to derivatives. Because it's going to turn out that because the derivative of sine x is whatever it is, the derivative of cosine x is going to be equal to its opposite, because these two add up to the constant. Yes, sir.
So eventually, if we want to find inverse cosine, we just do pi over 2 minus sine x.
That's right. If you have the inverse sine of x,
We can just take
then
that
you
from
can
pi
take
over
it. That's right. You can just subtract it from pi over 2 to get the inverse cosine of x. That's exactly right. And that, what that's saying is that the two angles in a right triangle are complementary to each other. Okay. Let's actually do a little bit of derivatives. This is our goal. Another way of putting this question is, if y equals inverse sine of x, then what is dy dx? You can see that these two questions are the same question, just written in different language. It would be lovely if I could just cheat and say, oh, that's got to be the inverse cosine, but that doesn't work, unfortunately. Wouldn't that be nice? But you can't, and it gives you the wrong answer. He was hoping. He had that in his mind, but it's not going to work out. So to answer this question, what I'm going to do is I'm going to get rid of the inverse sine, because I don't know its derivative and I don't know how to get it. I'm going to take the sine of both sides. And when I take the sine of both sides, then my inverses cancel, because that's what inverses do, and I get x is equal to the sine of y. If y is the inverse sine of x, then x is the sine of y. And now I can differentiate this implicitly. Using my implicit differentiation, I can take the derivative with respect to x on both sides. Easy, yes? On the right-hand side, d dx of x is 1. Yeah. On the left-hand side, d dx of sine y is
Cos y,
times
y prime.
dy dx. That's right. And hey, would you look at that? I'm looking for dy dx. I've got dy dx. No problem. Ta-da! Notice the inverse function theorem happening here. It's 1 over cosine of y, 1 over the cosine of the inverse sine of x. This is a perfectly good answer. However, because the original question was given to me explicitly, I would like to have an explicit answer for this. This is an implicit answer, and it's perfectly correct. I'd like to be able to rewrite it explicitly by giving it in terms of x.
You just sub back in sine inverse of x.
Yep, and then do our right triangle analysis on it. That's exactly right. So the answer to your question, when will I do that right triangle analysis in real life, is right now.
This doesn't count.
Oh, it doesn't count because
Math.
we're not real or something, I guess. I don't know.
We're all just illusions.
But you know what I would like to do, instead of the right triangle analysis, because we're short on time, I'd actually like to do it a little bit easier way by appealing to your trig identities. What do you know about the cosine of y? Well, isn't it true that the sine squared of y plus the cosine squared of y is equal to 1, is equal to 1. And so therefore the cosine of y is equal to the square root of 1 minus sine squared y, at least for the first quadrant. And I know what the sine of y is. The sine of y is equal to x. So that if I come back to my expression right here, and replace the cosine of y with the square root of 1 minus sine squared y, and sine y equals x, I now get an explicit form for the derivative of inverse sine, which is 1 over root 1 minus x squared. Now, calculus students everywhere need to be able to derive these. Why? Because you're not going to be able to remember them. Doesn't that look complicated? That looks complicated. I'm not going to be able to remember that. So I need to be able to derive it. So let's walk through how the derivation goes. We'll do it all again. The key moves up. We begin with y equals inverse sine. We don't know the derivative for inverse sine, so we clobber the inverse sine. What function clobbers inverse sine? Sine. So I take the sine of both sides. That's our first key move. Now that I've done this, these cancel and give me x back. Now that I have a function whose derivative I know, I can differentiate with respect to x on both sides. And the differentiation with respect to x on both sides gives me cosine of y outside times dy dx inside. And that equals the derivative with respect to x of 1, of x, which is 1. So that dy dx is equal to 1 over cosine y. This is an implicit answer. It's perfectly fine. But I would like an explicit answer. And so I use the Pythagorean identity to replace cosine y with root 1 minus sine squared y. That's a move that we're all familiar with. And sine y is x. And I'm done. So that's actually not so bad. But you can see that you're going to have to practice it like 2 or 3 times. And tonight would be a great opportunity to do that. I think we have just enough time to do the derivative of inverse tangent using the same idea. Let's see if we can. So here's our problem. We'll see if you can beat me to it. You know how. I take the tangent of both sides to clobber my inverse function, and I get tan y is equal to x. I now take a derivative with respect to x on both sides. What is the derivative with respect to x of tan y?
Secant squared.
Secant squared, not x, but y
dy.
times dy dx. And that equals 1. So that dy dx is equal to 1 over secant squared y. Very good, very good. Do you know any trig IDs that involve secant squared y?
No. That equals
You're supposed to.
cosine squared.
Oh no!
1 minus sine squared.
It's that, when will I ever use this in real life to come back to haunt you?
Tangent negative 1.
It equals something, and you don't know what it is because you didn't learn your trig IDs.
It's
No! No!
Cosine squared is
It's
that?
cosine squared.
It's not. I mean, it is. but
Cosine
that is- What is hint?
1 minus sine squared.
I'm looking for something in terms of tangent.
Oh.
1 minus tangent.
1 plus tan squared equals secant squared.
Exactly so.
Just take the cosine squared, the sine squared equals 1 and times it by
Cosine squared sine is negative 1.
If you don't remember, then it's all Okay, I'll stop.
And because tan y is equal to x, we are done.
Oh, yes.